Example 1.4.3, the amount of heat energy it takes to change the temperature of a substance by a given amount is called the specific heat of a material, C sub P, and it is measured in joules per kilogram Kelvin. The amount of heat taken by a material or absorbed by materials found from the formula heat energy is equal to mass times specific heat times the temperature change, temp final minus temp initial. And we should also know that mass can be calculated from volume times density. Our problem is that we want to assume that the heating of an electric tea kettle has a constant resistance of 100 ohms and it is supplied by a 240 volt DC source. The kettle raises the temperature of 1 liter of water from 15 degrees C to 90 degrees C, and that took 10 minutes and 52 seconds. Now I'm asking you to determine the efficiency of the tea kettle. There's one other constant we need to know, and that is the specific heat of water at standard temperature and pressure is 4,190 joules per kilogram Kelvin. I know there's some new concepts here, but hopefully this example will make those clear. They're pretty simple. So we're going to start by writing our givens. The first is that this electric tea kettle is really just an electric circuit. It's a 240 volt DC source connected to a 100 ohm resistor. So that's the information that summarizes the kettle itself. Now we need to know something about the water that's stored inside the kettle. So the first thing we were given was the volume, lowercase v, it was 1 liter. We know the density of water at standard atmosphere is 1 kilogram per liter. So that's a universal constant. The next thing we know is that this water went through a temperature change, so the initial and final temperatures were given. The final temperature is 90 degrees C after it's been heated, and the initial temperature, T initial, was 15 degrees C. Finally, we know that that temperature change took some time to heat the water up, and so that time is 10 minutes and 52 seconds. So those are our givens. We've been asked to find the efficiency, which you'll recall is given the symbol eta. That kind of looks like the cursive N in the Greek alphabet. Solution method. Remember, the formula for eta is just the output over the input. If we're looking for energy efficiency, it's energy output divided by energy input. So we need to calculate those two, the energy output of the system, which is the energy that's been stored in the water, and we have to calculate the input energy, which is the energy used by the kettle. So input energy is going to come from that DC circuit that we see up there, and the output energy is going to come from the formula that was given in the problem statement for energy stored in a substance when it goes through a heat change. So pretty straightforward calculations. I'll start with En. The electric energy, you should remember, is just real simply power times time. So how much power did something consume and how long was it on for? Energy is power times time. That should be in units of watts times seconds, and our time wasn't given in seconds. Capital T was given as 10 minutes and 52 seconds, so we need to convert T over to just seconds. So 10 minutes and 52 seconds is going to be equal to 10 minutes times 60 seconds per minute, and then we add 52 to that, so we get 652 seconds for the time the kettle was on. So that takes care of the T in that formula. Now we need to worry about the P. P comes from a variety of circuit calculations. You can know the current and the resistance, I squared R, or the voltage and the resistance, V squared over R, or the current and the voltage, I times V. Those are all the standard formulations. You look at our circuit though, and you see we have a voltage and a resistance. So we could use any of those, but the quickest way is to just take 240 volts DC, square it, and then divide by the 100 ohms. So 240 volts squared over 100 ohms is going to give us our circuit power in watts. Do that calculation real fast. And it is 576 watts. So now we can calculate energy just by multiplying those two together, the 652 seconds, which was how long the circuit was on, times the rate of energy consumption, 576 watts. So 576 times 652 is going to give us our input energy, and since it's watts times seconds, that's units of joules. So we get 375,552 joules as the energy input into the tea kettle in the form of electricity. Now we need to solve for the useful energy absorbed by the water, so that's the formula H equals mass times specific heat times delta T, the temperature change that we went through. We weren't given mass, however, so we need to calculate that, and we know that mass is equal to volume times density. And we were given a volume of water. We were told that it was a liter. We also need to calculate delta T, which is just the final temperature minus the initial temperature. So H is going to be volume times rho times C sub P times TF minus TI. So we do that calculation, and you're going to get 1 liter times 1 kilogram per liter. So that's easy conversion, is that a liter of water weighs a kilogram, multiplied by the specific heat that we are given, 4,190 joules per kilogram Kelvin. We can see that the kilograms are going to cancel there, and we'll be left with joules per degree Kelvin. Unfortunately, our temperatures were in Celsius, and we needed them to be in Kelvin for these units to cancel. So our temperature final was 90 degrees C, and our initial temperature was 15 degrees C. So we should convert those over into Kelvin before we take the difference, and that way the units would cancel. However, there is a little trick to that, and that is that Kelvin and Celsius are related by a very simple equation where they're just offsets from one another, 273.15. And so if I converted both TF and TI over to Kelvin, the 273's, once I took the difference, would just cancel. So long story short, the difference in degrees Celsius is the same as the difference in degrees Kelvin. The absolute temperatures are different, but the difference is the same. So 90 degrees minus 15 degrees is 75 degrees Celsius. That's also 75 K. Now don't think that 75 K and 75 Celsius are the same. They're not. This only works because it's a difference calculation. Anyway, I do that math, I get 314,250 joules. So now it's just a simple matter of throwing those two calculations into my formula for efficiency. So the output into the water was 314,250 joules. We already determined that the electric circuit used 375,552 joules. I need to multiply that by 100% to convert from a decimal to a fraction, and we're going to get a value of 83.7% for our final system efficiency.